Oh, right. Actually, just in case you think it's too frightening, this talk is really about how inverting the Laplacian plus something small implies everything, proves the theorem. Okay, that is the technical part from PDE in here is actually not very much at all. I mean, so I mean, and maybe so the whole trick is to figure out why the geometry gives you PDE that's easy to solve. Yeah. So let me say that there's sort of a philosophic piece because there's the algebraic geometry, which leads you to the differential geometry, which you actually heard at least last week, geometry. And that leads to the analysis. And actually, just a comment about actually how this actually works. How does the analysis help you? Well, the analysis predicts the existence of things that you can, for differential geometry and therefore algebraic geometry. I mean, if you understand this relationship, I guess we better put little arrows back here. But I don't know how we've done there. But what the analysis is doing is predicting the existence of things which can exist in certain situations, and therefore so let's see. Oh yeah, here we are. And so actually, let me start with a completely different notation. And I apologize, I can't use your notation. The problem is that I've been using this notation for 40 years, and which, I mean, most of you are younger than 40 years, so you understand that changing my notation at this point is, so you're going to have to change yours, you're younger, okay? So my manifolds are M. This is, in this case, it's a Riemannian manifold. And in fact, and of course, which you know, Hermitian-Einstein manifold is a Riemannian manifold. So, M is a Riemannian manifold. But in fact, the Riemannian structure is not important in anything I say, because all the estimates come from local estimates, and you can do them in small enough balls that the metric looks like a Riemannian manifold, and there's you get some extra little constants floating around from the, and I'll point out to you where that happens, okay, and why it's not important, okay, and and P over M is a principal bundle. And the bundles that are important for us are the automorphism bundle of P, which is I mean, for those of you who aren't really familiar with the differential geometry, here the fiber is actually the group G, but only with multiplication on one side. Here the fiber is the group G with multiplication with a conjugation so just for those of you who, I mean, and then add P is the symmetry group. Actually, I do it the opposite way from the way people do, so that I don't get a minus sign all over the place. So I mean, so when you see the formulas, I mean, I actually not quite the representation of the gauge group is inverted from what you usually. I'll tell you, you'll see, yeah.
So the fibers of
the Lie algebra.
groups and the fibers of HP are Lie algebra.
Lie algebras, right? Sorry. Thank you. And so the question of and also we can actually make all sorts of associated bundles to this, and the ones that we're concerned on are the are tensored with the product. So in other words, well, I'll explain. So the covariant derivative is a okay, sorry, before I do that I have to tell you. And the gauge group G is, and I write C infinity, actually we can of course make as long as the gauge group consists of continuous functions, everything makes sense. At some point your gauge group might not have continuous functions in it, and that can be a little bit disturbing. But that's of the automorphism bundle of P. And the Lie algebra of the gauge group is, again, I write C infinity, remembering as long as it's C0, you're okay, of the adjoint bundle. And this is the Lie algebra of this group. Okay, and now we actually need, and here I'm only going to use one indices, the of a bundle E is equal to wedge K. So exterior product with E, which is a bundle C infinity again. And again, you're going to find that we're going to drop the C infinity requirement to do the PDE. You can't do PDE in C infinity. I mean, it's not, you can't, you have to use the spaces that are allowed to PDE. And so the one that you might like, which is the continuous functions of some sort, is terrible. So when I write this here, we remember we can actually change that. But that we're only doing locally. And so the covariant derivative, let's see, this is not going the right way here.
Sorry, what kind of structural group may I think
What?
What kind of structural group may I think do G and R?
Oh yeah. There's no. G is easier to write than SUN, and I need a U1 at some point. So, what? It's compact. I'm sorry. Very important. I actually meant that. That's in my notes to tell you. And it's, of course, the goal is to do this for non-compact groups, but and I don't think we have. And there are things you could do for this. So the gauge transformation is actually a map from. And I write C infinity, remembering that we can change the C infinity to sections of E to wedge to T star M tensor. C infinity functions to omega 1 of E. Right. And I should point out to this that this is an affine space. This is space. That is, if you fix a connection D naught, then gamma is D naught plus A. And A is actually the difference of two connections, which is A, is a tensor. Okay. So if for those of you who want to know where the difference of two connections is a tensor, okay? And now, so far there's no geometry in M. So the curvature. So the curvature right, sorry. Oh, I got to tell you what D is. D is now a map from. Let me say this. By extension with the Riemannian metric, the connection actually will map gamma k of E to, and the problem is this does not go, it goes into this and there's a projection of this k of E, no, this is here. And there's a projection of the objects in here. Actually, I should write C infinity here, but we'll do that. And the projection of this will go into gamma k plus 1 of E, omega plus 1 of E. Okay. So we'll call this composition D, which is your exterior differentiation. And it's important, it's very important that it's not the same as Nabla, okay? So we really want to distinguish what they do. And the curvature is equal to, I'll write D squared of D squared, right? And this will turn out to map the gauge group G into wedge 2 T. Okay. I guess I got that right. What?
I mean,
it's a section of this bundle.
yeah, but you have to erase one G of the. You don't have G on the left and on the right. The G of the end of
Oh, I guess that's right. No. D squared, which that's N. There we go. I got it. Right, and this is add. Sorry. Add P. Okay, there you go. That's what. And so now we come down to the geometry of M, which enters. But as I said, it's in the geometry of M. And of course, the place where the geometry of N enters is where we want to take the adjoint of D. So in fact, I don't need to write that. D star is now going to be a map which takes the omega k plus 1 of E of add P to omega k of add P. And so it's just the dual, it's minus the dual, because I'm a mathematician, and my D star is actually, D star of F is actually D1 F1 plus D2 F2 plus D3 F3, so forth. So it's not minus, which is the formal adjoint, okay?
What do you use to define the star?
We use the Hermitian metric. That is, this is the same thing that defines the D star operator. So it's the, yeah, right. So you just you use the formulas that you have for tensor product and the D star that's defined on the base to get the capital D star. Okay, look. Why do you need it? Oh, by the way, and also
Probably you need to have an adjoint operator.
You need a metric.
To get a scalar product of your function
Yes, yes.
Yes. And so how the R and then
The Riemannian metric and the so I've chosen an inner product on the Lie group.
yeah, this is
Sorry. That's actually again not important enough for me to. It actually will come up in some cases, but for all the stuff today, all these choices of things like the
metric really important, or is it only the volume form here?
is the metric.
The metric.
It's definitely not the volume form. Okay, that's okay. Now so the important thing that comes from the geometry of M is the Bochner-Weitzenböck formula. Okay, and so in this case, we have actually two definitions of the Laplace operator, okay? We have the definition which comes from, again, I'm taking minus the formal adjoint. And the Bochner-Weitzenböck formula says that the operation that I get from the full covariant derivative is related to the operations that I got from D and D star plus D star. And I'll just write F. There's a curvature term that you have to figure out. It's a little bit different in every dimension. And then there's a curvature term, this is from the base. Now, this term is important because we're trying to estimate F. This term has an estimate on it already. So anything that comes from this term is not going to affect the analysis in any way whatsoever. I mean, unless you're trying to prove, well, and in fact, exactly I mean, there are places where this thing is very important, right? But not for anything that I'm doing today. Okay, that's term is lower order, and I can basically assume k is 0 for everything I do today. Okay, so we're interested, and I don't. I'll write. Right, and let me just say something for a moment because I don't actually know exactly what we want to do. I should have looked at the Simpson stuff, but I didn't have. I was so busy thinking about how to explain this that I didn't have time. So I don't know. We can also have a Higgs field, phi, which is a section of the bundle which goes into some associated bundle. Goes into. I'll just write E tensor wedge K T M. We can have Higgs fields that map into associated bundles, okay? And so what I say goes for a lot of these integrals. Some of the cases where I say something about them, you see that the Higgs field won't matter, and I'll put in a right-hand side, which I tell you comes from the Higgs field when you're actually doing an estimate with the Higgs field. So, but usually that right-hand side that I give you is not important. So, so the kind of functionals, and I'm only writing down this, is that it's much easier to plus. So the Yang-Mills Higgs functional is something of the form, and I'll just write d phi squared plus. The Yang-Mills Higgs functional might be something like this of phi. And so the Euler-Lagrange equations for that functional, I'm not doing very well on the boards here. Okay, we'll go over here.
So what is the Higgs field has values in
It has values in some bundle that you're writing an equation down, and you're going to couple Yang-Mills to something else, right? Which you're
values in the Epsilon bundle, not in the bundle.
Right, I can take any associated bundle I want. Yeah, I mean.
What's the last term? There's something, the Q of Q.
Just some function that's Q of phi, sorry. Okay, good. Okay. So it's an add invariant function on the appropriate fields. So the Euler-Lagrange equations for this one, and I just write this out just so that you get an idea. And I'm going to is d star f is equal to, and on the right hand side you get something that's actually you actually get a term. You have to figure out from the coupling of Yang-Mills fields with. And then you get phi, d phi. And this is just some field, which I'll call T. And the right-hand side is basically lower order in all the examples that I know about. And the equations you would get on the phi field are d star d phi plus d star d star phi plus, and now we have a lower order q plus q, some q prime of phi equals 0. And again, the important parts of this integral are this integral. Important parts of this problem are this problem and this problem. Okay, this part. This is all. In the examples that I know how to treat, those are all lower order. Okay. So we're looking at what I'm going to talk about today is for the Yang-Mills functional, but let's see, how do I do this? So the first, I'm sorry, I missed part of my talk because I didn't tell you. So we're always going to be working on a disk B, rho, which is equal to the set of x, such that x is less than or equal to rho in some coordinate chart, which sits in M. And as I explained to you, certainly the rho is small for all these examples. The whole idea is to take a small neighborhood and make an estimate in that. So I'll talk about the size of the ball a little bit later when we get to some of the analysis. But now if you have a ball like this and you choose a trivialization, that is, and I just simply tell you that this, now I'm just choosing an example where P rho cross G, and of course add P is B rho cross Lie algebra and G and so forth. So in this case, I should write down what everything looks like. That's the point, because we're going to work in that. And in this, so this is what you never do in algebraic geometry. So I find you may actually write it in coordinates. But this is choosing a coordinate, and it shows coordinate on the base and the bundle. And now in this form, nabla is D plus A, where A is a one form with values in the Lie algebra, okay? And F is equal to D A plus, and I'll write the 1/2 A bracket. This is a wedge and a bracket together. And if you want, in case you wonder where the half goes, it's quite easy. That is A bracket B is a I in the coordinates I j is a I b j minus b I a j, which is a well-defined object. This is the Lie algebra bracket if you check this out, that has to be a half there. So in case you're always that's d plus a. The gauge transformation S is simply a map from the ball into the automorphism bundle to G, right? With the is a gauge transformation. This is this has a left and a right, and in my formulas, the gauge transformation acts as follows: S star of my nabla is equal to S composed with nabla composed S inverse. So that's the answer to which side I'm taking my principal bundle, okay? And I don't know whether it's the left or right, okay? And if you work it out, this is D plus S inverse DS plus S inverse AS. And you see why it's not a tensor is because this term is appearing in the change of. And it's easy from this to see that S star of induced on the curvature tensor is just S inverse FS. And may I remind you that, I mean, you can use all sorts of things, but this is what's not true in the complex case is that F in absolute value is S star F. And in the case where you're working with a non-compact group, this would not be true. So everything goes wrong. I mean, that's basically the problem, right? So let's see if we can't do this a little bit better. Okay, so now we want the Euler-Lagrange equations. And by the way, you see the Euler-Lagrange equations are gauge invariant because the integral that I'm taking is gauge invariant. So I don't need to, I don't have to go through. And the Euler-Lagrange equations for Yang, Mills, Higgs. I just write that down. There's something like, D star F is equal to, and I'll write down a right-hand side, and I'll write this, and this is lower order. Is that what I called it before? Yeah. No, this is, I don't know. I'll just write something of lower order. And D star D plus D star phi, which is, by the way, I'm writing this down so that so you have a term, and again, this term is never important. This was kappa, I guess. Kappa is equal to 0. This is not an important term, and that one is an important term. And now, so now the question is, what do we do to get estimates? Okay, And the point is I have to go to the local neighborhood. But the answer is that I actually know what to do, because we already solved a problem. We already solved a problem. We already know the solution to the problem. And the solution to the problem is to choose a good gauge. And we already know how to do Hodge theory. And Hodge theory is what appears when the group is U1, is abelian. Okay? And in Hodge theory, and again, I'm just looking at the curvature equations. And the Lie algebra had G is I times the reals. And so in this case, my connection just looks like D plus I little a. I'll just call it like that, where A is now is actually just a one form. Okay? A is a one form. And the curvature F is equal to I dA. No brackets, right? And so the Yang-Mills equations or whatever are going to be D star F equals 0. And again, they can have a lower order term. That's actually not, no, we're doing estimates, and so we tend not to we're not using any special form. And now the question is how do we find an estimate on A? And the answer is that we choose it to be co-closed. We need gauge transformations. So that's S star. S is equal E to the IU, where IU is a real valued function. And again, we're only doing local theory here. In general, everything. By the way, I should say the add bundles are all trivial. The principal bundle is not trivial, but these bundles are all trivial, okay? Because they're glued together by conjugation. So the gauge transformation, e to the IU, and S star of D plus A.
So what we're doing now, we have a connection on this U1 bundle.
Yeah.
We're making a gauge transformation to make it as small as possible.
That's right.
Estimating it in terms of the curvature.
That's right. Right. So S star D plus A is D plus IA plus I DU. Right? So the new expression for curvature in a different trivialization. Remember the bundles are all trivial, but we can change. Is just to get some gauge theory, and so obviously we know what to do to make it into PDE. I mean, to actually define Hodge theory and so forth, you have to make this into PDE, which means you need an estimate, which means you need to choose A. And you know how to choose A because you simply choose D star A plus DU equal 0, which and we solve this, and we know all about the solutions to this equation, and notice that dA is equal to F is either and dA is equal to F dA plus du. Actually, let's call this A bar, and there's A bar is equal to F, which is either 0 or controlled. That is, we know what F is. And so this is now a PDE, D star A bar equals 0, D A bar equals 0, which is elliptic, which, I mean, if you believe anything from PDE, you'll understand that people can understand this equation. This is, so we know what to do. We know that when we go up here, We would like to solve, and I'll tell you what you might like to do first, and which will not work. And that's, so what you would like to do is to choose, what you think you might like to do is that you have a connection D, nabla, which is equal to some base connection plus A. And remember now A is a tensor because it's the difference of two connections. And I might want to say, well, clearly I have an estimate on the curvature of nabla.
But we're no longer in the U1 case. Are we still in the U1 case now?
No.
Okay.
No. I'm explaining why it won't work in the U1 case. Okay. Yeah. So, right. And so I'll just write. So F nabla is this dA. I'll write is F nabla naught plus nabla. Let's see, nabla A dA plus A bracket A, where this is the tensor now. It's the difference of two connections. And dA is, so the estimate on curvature should give us, but this is not a very good term, but should give us an estimate on A if we ask for dA star equals 0. Okay. Now, however, actually, D naught or D naught. Actually, check the differences. This is, you don't have a equals 0. So you immediately check. This is just too nonlinear. This term here messes you up completely in trying to make estimates. Remember, you don't know anything about A to start with. You just know that A is in some space or another, but you don't really know anything about it, and this nonlinearity in the term messes you up. So this problem is solvable in the small. And in fact, when you're actually looking at perturbations of connections, that is, you're looking at a connection which is the base connection plus I'll write an epsilon b, and you want to know what a gauge transformation that puts the small bit in the equal to 0. In other words, it actually trivializes something in the tangent bundle to what we're doing, because we're making a small perturbation of a connection. And then that's what you do, is you actually set D naught star B, which is the same as equal to 0, right? So you set that base connection equal to 0. So we already know that we have to do that to make any sense out of what we're doing, is we actually have to choose this slice in the tangent bundle. So it's not a completely worthless viewpoint of how to go about it, but it's not going to work globally for connections that aren't close to something that I really understand. So the idea is that, well, you can't do it, and in fact we don't expect it to work. Well, it's not going to work. Okay, let's just put it that way. That's so what we're going to do is do this over a small ball, and that's why we suddenly get ourselves. We're only going to do this locally, okay? And so now we come to theorem 1. Okay. So the claim is that we have now. No, we have one more thing to do before I go to theorem 1, and that is, since I'm doing PDE, I have to talk about analysis, which means I have to talk about function spaces. okay? And the fact is you have to use a function space that you can invert elliptic operators on. So you can go and look for the series of whatever you like. And in fact, it's a very useful, I don't really know how, since we discovered that Morey spaces are very useful in higher dimensional problems. But the fact is that there was a clue in the estimates of why that was so. But every once in a while you have a problem and you think, well, if I had the right analysis space, the problem would just, evaporate and be trivial. And so I don't really know what to tell you, except that the spaces that I cut my, are the LP spaces, these are the set. And remember, we're going to be at a ball all the time. So you don't have to worry about the geometry too much. And this is the set of F such that integral F to the P is less than infinity, and that's the norm on the space. And LPK is equal to the set of F such that d alpha F to the P dx to the n integral 1 over P less than infinity for less than, we never use K bigger than 2 in any essential way, so that's, so these are the Sobolev spaces, and there's something very important to observe about Sobolev spaces, and this is very helpful in trying to understand what could possibly be true. So the point is that here the different sized balls are kind of a helpful thought process, okay? And so what you should do is you should actually look at let's take the integral, let's look at L1 P spaces and LQ spaces, okay? And the question is, what's the relation between something that's, now you know that if a function's continuous, that if the function is Lipschitz, you know it's continuous, right? So you know that, and similarly, you know from the definition that if P is equal to Q, this space is bigger, right? But the question is which one is bigger? And that turns out to be essential to all the calculations that are done. And it's kind of cute how you figure out what is essential. That is, what you do is you take the integral on the ball of radius rho of d alpha to f, what did I do? P, right? And we look at the integral of f to the q dx. And again, it does not matter, but let's put the dx to the n in here. Okay. And actually, these are not covariant derivatives. I'm sorry, I'm just making, these are multi-indices, okay? And what we're going to do is we're going to take these two things and we're going to transfer them to estimates on the unit ball, okay? Now, if we transfer these for estimates on the ball, you want to know how to do this. Well, y is then equal to x over rho, right? And then we take the ball of radius rho to the ball of radius 1, right? And so when we do that, and remember this derivative acts the opposite as the differential, right? And so we do know that this is dy, dx to the n is dy to the n times rho. Did I do this right? Sorry, I did this. Yeah, right. It's dy to the n. And remember, this acts as the opposite. So there's going to be a dy to the n and a rho to the n. And then here there's going to be a p minus p alpha, because the derivative acts the opposite from the one form in the derivative act the opposite in the. So this becomes rho to the n minus p integral over b1 of, and then d alpha, I'll call this f, and I'll write this in the direction y to the p d y to the n. And over here, we just get the term, we just get to the term f at this point isn't changing, and so we get a rho to the, and we better put a 1 over p here. And we better put a 1 over p.
Is it possible to formulate the statement that you are proving?
What?
Probably you are proving some statement.
No,
No?
I'm just telling you how to remember everything, okay? Because you're going to forget, because you're not an analyst, and you can't tell me automatically. And so I'm going to tell you how you figure it out,
Well, maybe
okay?
Okay, so the function is more summable than you're assuming because the derivative has the summability of the function. That's the upshot.
Right.
And she's getting like what is the optimal that you can get, like the highest view, which is Sobolev from that.
But is it possible to formulate this optimal statement before the...
Yeah, I'll tell you what the theorem is, okay? I'll tell you what the theorem is, but that's, okay, so you look at this, right? And you want to estimate this in terms of this. Well, if it's true on the ball, it's true on the ball, a smaller ball, right? Because I just take a function that's 0 on the boundary, I write down the estimate, and then I rescale it down. And so if it's true on a ball, it's true on a smaller ball. And so I really have to just decide which one of these guys dominates. By the way, I don't want to blow it up. I mean, I don't want to take a ball and take it the other way. I want to take a ball to take it down. So the theorem is that if this, the theorem is that the theorem is that LP1, you can iterate it, is an LQ, okay? If, if 1 over n minus 1 over q is less than 1 over p. I have to figure. I haven't. Sorry, I'm clearly not. What? L. Sorry, let's do 1 over L2. This is 1 over p. I think I have it right. If inequality is compact embedding, which means that bounded subsequences in the smaller space converge in the larger space. So that's going to, we use that all the time. I mean, we use this, but I mean, the way to figure it out is to figure it out by checking how things scale. So it's associated to things like how they scale. And so it's associated with that is the scaling on curvature. So curvature is a 2-form.
I believe you want bigger or equal than 0.
What?
I think you want bigger.
I'm sorry, I can't. It is bigger than or equal to 0 because.
I mean, it has to work.
That's right. No. It's greater than or equal to 0. Sorry, I know. I'm sorry. I know these things so well that I can't. So the curvature, the question is, what happens to the curvature under this thing? Now, remember.
By the way, is it called Sobolev's theorem or something else?
Oh, it's got I'm sorry. I learned it as a graduate student as Sobolev's theorem, but it has a Russian name associated with it. And again,
Sobolev and something else.
It's something else.
Somebody.
What? Come in. It's somebody else.
I never
There is somebody. There's some other name associated with this. Right. Oh, right. Okay. So the curvature. The question is what the curvature does, and this is very important because remember the curvature. We're in local coordinates. Is d plus is dA plus a wedge a. So we can't rescale the base without rescaling a, because these terms won't match anymore and the curvature won't change. So we're forced to actually change a and change the curvature, and curvature changes like a 2 form. So it's very important to notice that the integral of curvature over a to the p dx to the n integral x less than or equal to rho is actually equal to the integral I have to, this is the integral of rho to the, what's it, n? I'm sorry, minus 2p. Yeah, right, integral x y less than or equal to 1 of the new curvature to the p dx to the n. Okay. So we want this term, we want to do an estimate in a small ball, okay? But we can't do estimates in small balls. Even as an expert analyst, I lose track of all the estimates and the scaling of the inequalities. How to invert the Laplacian? What's the normal inversion of the Laplacian on a small? I have to do it on a ball, a regular ball. And so I want to take what I'm doing and I want to transfer it from a very small ball to a standard size one where I can understand what I'm doing. And that's what I'm going to be doing in the entire talk, is looking at things on small balls and looking at bigger. And we actually don't want the curvature to get bigger. We want it to get smaller. Sorry, I have this backwards. Rho is small, sorry. We want the curvature to get bigger, smaller, not bigger, right? And rho is small. So we want 2p to be greater than or equal to n to do analysis. So we're faced with the fact that if we want to do some analysis in a naive sense, without getting more sophisticated, we're going to need estimates on the curvature in a space which is better than scale invariant, shall we say. I mean, so that tells you where the dimension 4 comes in, right? Because in the dimension 4, p is 2, and that's the scale invariant case for a curve, is the norm of the curvature. So the n equal 4 is the scale invariant case, and we know from some experience that that's the interesting case, that the interesting things will happen. Now, let me say there are other norms that are scale invariant. And you want to know, in higher dimensions, can you actually get any of them? And the answer is yes, there are other norms that are scale invariant. And when you have a scale invariant norm, you have a lot of hope for getting the estimates that I'm talking about today. But those spaces are more complicated. And they come, by the way, since I assume you're going to have this, they come from monotonicity formulas. That is, they come from estimates that you have on solutions that are that are special to solutions. And when you have those kind of estimates, if you can get something small in a scale invariant norm, basically what I'm talking about today will work. Okay, so let's see. Okay. Now, okay. So now we go to theorem 1. Sorry, I got there. So the claim is that P in n over 2, so this is an n-dimensional theorem. There's nothing special to 4 dimensions at all, except that you're not going to get the right estimate on f. So if you're actually minimizing the Yang-Mills functional, or for some other reason you know what f is, then you can say that if f on a ball, any ball actually, I haven't, is small enough. And notice that if f n over 2 is bounded, I can actually assume that ball is radius 1 because it's this problem scale invariant. So but I state it that way. So and note an A here. There's an important point here is A. The A in the original f has to already be in the right Sobolev space to define curvature in that space. So this is actually a bit tricky because that's what goes wrong in the removable singularities theorem is you don't have an A in the right space, so you have to do something different. But if A is in the right space, then you have a gauge transformation, which is remember this is the A that comes from the gauge transformation. The conditions on A are that it's co-closed. And by the way, here, you might as well do this in Euclidean space, because if I have an estimate in a Hermitian metric, I just by a little bit of, in a Riemannian metric, it's so close to the Euclidean metric that I don't really care about the differences. It's in a Coulomb gauge, which is what we knew from Hodge theory we had to do. Right? It has what are called Neumann boundary conditions. That means that A is a one form, and when you restrict it to the normal direction on the boundary, it vanishes. So if you look at Hodge theory, you'll see there's a whole theory of Hodge theory where you actually can put boundary conditions on things like the normal. So this is the normal derivative of A vanishes on the boundary is this condition. And the gradient of A, here, I don't mean nabla because nabla is a connection. I mean the actual real derivative gradient of A is bounded by the curvature of that we had a bound on for all P where all this makes sense. I mean, I might not. The gauge transformation is actually not quite continuous necessarily, because this is not quite enough. It's in LP for all P, but it's not, and it's in L infinity, but you have no estimate on the norm of continuity of F if you just started out there. And S is unique up to a gauge transformation. And again, the question is how do you prove this theorem? And you prove it by the first theorem that every analyst should learn, but I fear they learn fancier things like the Atiyah-Singer index theorem and stuff like that before they learn this method. And this is the continuity method. So this is the method that Yau solved the Calabi conjecture. It's the way you solve this problem. And so the continuity method okay. And so the continuity method proves three things. It proves I. This is it's open, closed, and space is connected. And for some reason or other, this was the hardest for me to figure out, was 3. The space is connected. Okay, so what's open mean? Open is just the implicit function theorem. Okay, so open is just the implicit function theorem, and the linear we're solving d star plus S inverse d star ds just to plus near the identity. So you want to solve that near the identity, and that's the equation Laplacian of u plus d star a bracket u equal b d star b, where b is the infinitesimal change in a. So I change a very slightly, and I need to invert this operator, and this operator is invertible if a is sufficiently small. A sufficiently small is a hypothesis of the theorem, and so we are really just solving Laplacian u plus something small is equal to something on the right-hand side. So you have to work out its borderline. That is, A must be small in the space H1, which means, sorry, A has to be small in the correct space. I'm sorry, I'm not in 4 dimensions. But A has to be small in the appropriate space. But that's all built into the hypothesis of the theorem, namely that we have to have an estimate on the gradient of A, which is with P equal n over 2. And we know we have that. So the gradient of A is small in appropriate space, and we can invert this operator in the space. And in fact, we can invert this operator in any LP that we want. So this is, in other words, this is Laplacian plus small, which is small. Again, you have to work out exactly what spaces go in what dimension. Is 0. And small is, let's see. Do I have anything insightful to say about what small is? Small is actually L4 in this d star A is 0, so this is an A du. In order for all the arithmetic out in 4 dimensions, A has to be small in L4, but that's estimated by all the conditions I wrote down. Anyway, oh, right. I guess I should point out to you it does have a kernel plus A. D star A is 0. U is equal to D star B. This must be, I forget what this one is. Sorry. But in any case, this has a kernel of constants. So I'm not, actually, I can't quite remember why the right-hand side is, it's the solutions. Oh, this operator has a kernel, the constants. So that's, so, what? Oh, okay. The one form, okay, is tangential. The normal component of the one form. That's a Neumann condition. The normal component of the one form vanishes. Okay, sorry, I don't. I can write down all the numbers there, but just I assure you that if you work it out, A is small in the right spaces, and we can invert this operator. If A gets larger, we can't invert the operator anymore. So that's okay. Okay, and closed are just so that's so the implicit function theorem says we can invert this. So this is I. 2, as usual, closedness is always from the estimates. Okay.
So what is supposed to be open and closed?
the set of A that satisfies this condition. Okay? The set of A that satisfies this condition is open and closed. Okay. And so this is, that's just estimates. And the estimates are in the theorem right here, because we have an estimate on A, and we can take a weakly convergent subsequence, and the estimate will still be true, and we're in good shape. And the final thing is about how do we continuity? Well, actually, that you could have a very smooth situation with an A that was very, very far from small. The question is how you're going to connect it to an A that's small. And of course, here we are. All we do is we take a very small neighborhood. We actually use that expansion that takes a small disk to a larger disk. And if we go small enough, the curvature, everything is small on that disk, and I can just use the implicit function theorem. And then the expansion by rho, that is, remember I said y was x over rho. And we look at a ball of radius rho, and we transfer the problem to a ball of radius 1, and we solve the problem on the ball of radius 1 by solving it on the ball of radius rho by solving it on the ball of radius 1. And this we want to say it'll give us a transformation that'll take A into a multiple of A, and you could start very small, and you have a continuous family of expansions in rho, and so you get a one-parameter family of problems that you can solve along that curve. Okay, is that clear? I mean, so the scaling is very important. We have to know that the problem scales properly, which is why you can't do the problem in L2 in higher dimension than 4, right? Because this step would particular, this is by rescaling. Okay, so that. You happy? Want to ask any more questions? Because I'm going to leave this. I'm going to use this automatically, and and you probably didn't really want to know all that, but that's what.
I still don't understand what is supposed to be open and what.
Oh. Actually, the answer is that there's a little bit of trickiness, okay? What we do is we take this problem and we actually make a very small perturbation to make A very smooth. And so we look at the A in the L A in L2, 1 that satisfies all these conditions. The A tilde and L2, 1. The A that satisfies these conditions is open and closed, okay? And so the set of A that satisfy this is an open condition by the implicit function theorem. That is, if I have an A that solves this and I perturb it slightly, I use the implicit function theorem that says nearby I can find solutions. If I have a sequence of things that's converging, and it only has to be weakly converging, actually. I have a sequence of things that is weakly converging, then the limit will actually satisfy all these inequalities, okay? And then the point is the family, I have actually connectivity. That is, the set of things that satisfy the hypothesis is actually connected. And so then I can just use the implicit, sorry if this is so complicated. Well, the point is that when I actually look at the expansion around a very small neighborhood, it's small. When I expand it out, it's the curvature to the n/2 power on a very small ball. And if I have something whose curvature to the n/2 is finite, if I look at a small enough ball, it's going to be epsilon. There's no you don't have any delta functions around. So if you look in a small enough ball, the curvature restricts to something that's very small. And so then I just connect it to the one I wanted to solve by taking the family of rescalings. Oh, sorry. That's...
And what about the uniqueness?
That's that'll follow from these estimates. By the way, there's no uniqueness, by the way. But the estimates, the uniqueness, if I require A to be small. Okay, there's no uniqueness. That's A is but unique under these hypotheses. That's no. In fact, you can show. In fact, you can show that if you take an A and you multiply it by something very big, that and D star A is 0, and you multiply it by something very big, you can show that that solution is not a minimum to a functional, which means that it's not going to be a unique solution. So anyway. Oh, you know, I suppose I could point out to you that the way not to solve these problems, because it is that you might think that by minimizing the size of A under all possible gauge transformations, that you might get a Coulomb gauge, and you do. The problem is that that's a harmonic map problem. Namely, it has all the illnesses and sicknesses of harmonic maps, meaning if you try to minimize A with respect to all the gauge transformations, you're going to get all the singularities of harmonic maps, and the singularities of harmonic maps start to go bad in 2 dimensions. So you don't really want to use the fact that this Coulomb gauge minimizes the square norm of A, the L2 norm of A under, I mean, that's kind of deceptive. You find, especially if you work in the calculus of variations, you're tempted immediately to okay, so.
You do find the smooth minimizer this way, right?
What?
You do find the smooth minimizer in this way.
Oh, yeah.
So a posteriori might be possible even by the direct methods. You just would have to develop a fancy regularity theorem for that case.
I'm not even sure that a local, well, I don't know. Well, I've always thought that was kind of an interesting question of, you know, but it's not one that anybody ever picked up on. So that's okay. Good. Okay, so we go on to the epsilon regularity theorem. Oh well, this is the regularity theorem. I won't state it. Well, I guess it is the epsilon regularity theorem. Epsilon regularity theorem. And the statement is that if right, and again, this is a dimension reduction. This is the ball of radius. I'm going to state this for the ball of radius 1. You realize that it's a scale invariant statement. So f to the n over 2 is less than this epsilon that we had up there that depends on the dimension and the group, because there's a group norm in here. And this is a metric. We have a metric here, and that's if A is in L n over 2, 1, and A solves, and Nabla solves Yang-Mills with a possible lower order term, then A is smooth in the interior. And this is involved radius. Since it's scale invariant, it's actually smooth on the whole thing, but I'll say B 1/2. Okay, and so how does this theorem go? This is just a straightforward regularity theorem. That is, we actually use the good gauge theorem, okay? And we use the Yang-Mills equation. The Yang-Mills equation looked like D star. Let's write down what it looks like. A plus, and this is the proof. Since, again, it's really just the Laplacian plus something lower, small that's lower order. So we write down D star D plus A bracket. I'll just write out to you so you see what all the terms are. Plus A bracket F A equal to, and remember there's something on this side, but it's smaller. So we don't really care what it is. And we have D star A equals 0 from, this is the A tilde from the good gauge theorem. Okay. And we now look at this problem. Now we don't have a boundary condition. That is, the boundary condition I gave you for A is not, we don't expect a boundary condition because the boundary condition was good for first derivatives, but it doesn't work for high. We don't have a boundary condition. We don't have enough information on the boundary, so that's why we only get interior regularity. And so we have an equation like this, and again, we write it all out. And we have something like D star D plus D star. Actually, we actually might want to use the Hermitian metric here, but then again, it's a fairly easy to change from the Euclidean metric to the flat metric, to the local metric. So it looks like D star D plus D star A. And now you can run through what the right-hand side looks like, right? And it's got a, let's see what it's got. So it's got a derivative of A times an A tilde. And it's got, what? A tilde is smooth. No, oh, sorry. So this is the, yeah. Implies, oh, then A tilde, sorry. And so I think I got all the terms of the sort, and this is actually equal to something on the right-hand side, which is actually small. So this is bounded, and we won't worry about that. And we look at it, and basically this is a Laplace operator. And again, this, as you say, this is the Laplace operator on a manifold, but it differs from the ordinary full Laplacian on which you get estimates easily by something lower order. So this is just Laplacian of A plus, and this is, I'll write plus some term U times A. I'll write even is equal to Q, and again, Q is regular, okay, so Q is, and U is made up of dA and A bracket A. Well, dA and A bracket A are in Ln over 2, which is exactly the right space that we can use to get estimates. So using this equation with U, this is actually small in Ln over 2. And that's the magic thing in the Sobolev inequalities that says that this is a small perturbation of this, that it's small in Ln over 2. So we reduce it again now. But now we don't have boundary regularity. So what we have to do is we have to cut off at the boundary and then write a right-hand side, which is, again, more regular than what I have in the interior. Then invert the Laplacian plus something small with the cutoff function, and then I get a better estimate on the interior in terms of the estimates I had on the whole space. In fact, in terms of the estimates I had on the boundary, in fact. So that's roughly, so we get, it's a problem of reducing the question to Laplacian plus a small term equals 0. And when you don't have a boundary condition, you get interior estimates, but not regularity estimates. Okay, is that? But we need a good gauge here. There's no, well, sorry, A tilde equals 0. Okay? Okay. So there's a corollary to this theorem. And the corollary is global. And I'll state it only in dimension 4 because it's not really of interest in the other cases. And so I'll make a, so the corollary. Suppose. So this will be my I'm counting. This is not an index. This is the sequence. And of course, is a sequence. I'll call them Yang-Mills type equations. Remember, we can have a right-hand side, Mills type equations. With f alpha m. Okay. Then there exists a subsequence. There exists a subsequence. Alpha prime. And a finite number of points, x1, xk, contained in M. Yes. Sorry. M is compact, right? Sorry, these are things that I take for granted. And M is compact. I mean, there are cases where M is non-compact when you could do things. And trouble with M is not compact actually turns out to be M minus the points is not compact. But the problem is that when you miss a bunch of points, you start having a little trouble deciding what that constant of the gluing maps is. And if you change the constant in the gluing maps and you come around in a circle, you might not match anymore. If you have too many of them around, you're not going to match anymore. So it's there's some problems in the cases where you need too many. Okay. And gauge transformations. S alpha, and I'll write these. These are sections of M minus x1 to xk to the add to the automorphism bundle. such that S alpha star of gamma converges to alpha on I'll even give it C I don't want to, let's just say C infinity, a loc of M minus x1 xk. This means if you take a compact set away from those points, you can get the convergence to be uniform, but if the but near the point you have absolutely no control, and the curvature to f, and let's call that infinity, okay. And now the curvature of the infinite limit is actually defined everywhere but at a finite number of points, right? So it makes sense to say that the integral of the infinity, the curvature of the L infinity norm squared is less than or equal to the lim if as alpha prime goes to 0 of the integral of f gamma alpha prime squared over m. Okay. And basically, this is the Lebesgue dominated convergence theorem, by the way. Just to and it is really true that this limit can be strictly less. Okay, there's many things that. So this limit, so it converges off finite number of points. It converges actually in this local C infinity topology away from the points, and gamma infinity is Yang-Mills on M minus x1 xk. Okay.
The connection you were seeking, is it all on the same principle?
Yes. Oh, yeah, yeah, but we don't have a principal bundle anymore.
Where is the
Because we took away the finite number of points, and we only have a bundle now on the manifold minus a finite number of points. So it's a principal bundle on a manifold minus a finite number of points. So if you have a principal bundle, you could go out a finite number of points and define it. But as far as I know, unless you have some pi1 around, if you take out a finite number of points in a bundle over a 4 manifold, you actually get the trivial bundle if there's no pi1.
You mean if the group has no pi1?
No, the manifold. Well, the group, no, the manifold. I mean, yeah. Okay.
So your connection has singularities at least.
That's right. So, I mean, if you want, it's a connection on that bundle, but there's no bound on what happens at those points. So we really can't regard that connection as a. So you could think of it as a singular connection with a finite number of points removed, if you prefer. But no, M is a 4 manifold. Okay, actually, so what happens if M, okay, let me just say, I threw away the P. If N is less than 4, we get convergence everywhere, okay? The point is if M is less than 4, because of the scaling, we have Yang-Mills, and Yang-Mills scales really well, meaning that if I have an estimate on L2, of the curvature on a 3-manifold or a 2-manifold, the Riemann surface. Let's take the Riemann surfaces because you're algebraic geometers and you don't do 3-manifolds. But anyway, you have a 2-dimensional manifold, and you have an estimate on L2 norms of the curvature. Then that estimate, all I have to do to get the curvature, the L2 norm of the unit ball curvature small, is take a small enough neighborhood, and then I actually get it automatically true. I don't really need the epsilon regularity theorem to get convergence. So for n equal 2 and 3, this is the points aren't there, and this theorem is true. For n equal 4 is where we see the points, because it's the scale invariant case. Okay. There's C infinity off those number of points, but they're crazy around those points. Right.
I don't understand. If you have the group U1, then the topological invariant, you have the first Chern class, which is in H2.
Well, this theorem is in the Nonabelian case. Okay, I'm sorry. No. We're not in U1. We know how to do U1. U1 was, kind of wiped off the map.
You need to fix the bundle.
Well, if it's any, okay, look, if it's any comfort to you, there's a theorem that says if you fix one of the lower, I forget, Stiefel-Whitney classes or Chern classes, that's preserved. That is, it's only the ones that actually sit in, that is, if you have some sort of structure, I forget what they're called now. I had a student write a thesis on this. But anyway, the bundle over the manifold minus a finite number of points still has some structure. That is, it still has some Chern classes. It just, but it doesn't. It's the. So those are the Stiefel-Whitney classes, for example, are preserved, right? And so you can say something about the bundle you get in the limit, but not a priori. Okay. Okay. So now to finish the theorem off, and I guess before I finish off, so now we want to remove those yeah. So now we're faced with the last theorem, which is that now it becomes a local theorem again. We end up with this Yang-Mills equation over a manifold minus a finite number of points. And we have this, an L2 estimate on the curvature, and we want to know, can we fill in those points? Okay. And wait a minute. Okay, so we might as well look at the ball of radius 1, because the L2 norm is scale invariant, and we might as well choose a ball along which the curvature is actually small, because again, if the curvature is in L2, if I look at a small enough ball, that the L2 norm is small. So this, and the L2 norm of curvature is scale invariant in this case. So I might as well take it a ball. And what I have, the theorem is that, sorry, I don't know, is that if we have a, is smooth and, so the claim is there's actually a connection. Oh, okay. And satisfies the Yang-Mills. Oh, right. And satisfies, sorry, Yang-Mills on B minus 0. Okay, so we have a smooth connection on the ball minus the origin, and we want to know we can fill it in. And the answer is that the answer says is that we can fill it in, but we actually don't know a priori what bundle, if you like, the connection is actually in. So and the proof is actually quite different. This is not the original proof, okay? Okay. But this, every connection. I mean, just a bound. Just a bound. But you see, okay. Okay, it's just a bound. Okay. And the first observation is that we can assume K is small by integral f squared b of radius rho less than some number, and this implies that the rescaled f bar squared b of radius 1 dy squared dy to the fourth. Actually, we're dx to the fourth. The rescaled curvature on the ball of radius 4 is less than epsilon because the problem is scale invariant. Okay, so that's the first assumption that we can do, is we assume that we'll prove it in a small ball, and then we can glue it together to whatever we're doing in the larger ball. And the second thing we do is we're going to use the Bochner-Weitzenböck formula. Okay, and this is and I wrote it down for you once before, but I'll write it down for you again. It says that the full covariant derivative of f is equal to d star df plus d star f plus and I'll write q. I mean, this is this q is something that's lower order, and we're assuming that we already know that that's a little bit regular, and oh, I'm sorry, I forgot what I was doing. Plus f bracket f, and then there's a scalar curvature term f plus q, and this stuff in here is smaller. That is, it's more regular than if you want to think about where this piece sits. This thing here only sits in L1, whereas this sits in L2. And L1 is not a very good space to work with and so forth. So we use the Bochner-Weitzenböck formula, and I'll just incorporate this into, I'll call this lower order. That seems the fair thing to do. Okay, well, you figure, yeah, okay, so that's a little exercise to figure out it is in the right place. Okay, that is where does this actually sit, right? The f is a two form, and so d star df is a two form, right? And so there's a two form here, and we got to contract on one of the pairs of indices. So there's 4 indices, and contract on 2 of them in some order. And because of the skew symmetry, it doesn't matter which order. There's no sign to this term or anything. So this is locally something like f k j f j l summed over j, which is a two form. We don't actually care what it is. We just want an estimate on it, to tell you the truth. That's why this is, as I said, there's no geometry in what I'm talking about. It's actually just PDE. So it's, okay. And so if you dot this with, take an inner product, and by the way, it's the inner product on the group, is inner product on the group and in the space. You'll actually get, I'll write out exactly what you get. You get the, take the dot product with F, which, so that's minus the trace, whatever, with F. And so there's some, for practical purposes now, I'm going to sort of ignore the geometry on the base because it does not enter into this argument. And so if you actually take the dot product and massage it a little bit, you'll get that the Laplacian of F plus right. Yeah. Let me do it into. This is the full covariant derivative of F. It's less than or equal to F cubed plus. I'll write just lower order, meaning I'm just going to ignore that term because whatever's there is not important in the equation. So, so if you divide this term by the absolute value of F and and use Kato's inequality, which is df less than or equal to the full. See, this is very important that you have the full covariant derivative here. This is not okay. So the derivative of the absolute value of a vector is less than or equal to the covariant derivative of the vector in norm. Okay? Does that make sense? Why is this true? Well, df is equal to.
Gradient be on the right-hand side?
This is actually grad, if you like. Df is equal to the covariant derivative of f dot f. Makes sense? Sorry, these are things I can't explain because they're built into my.
This gradient is of absolute value of f squared or
F, because I divided. Sorry. Where's a half somewhere? No. There's a 2 here.
Yeah.
Okay. Sorry. This is the sort of thing that when I listen to an algebraic geometry course, you guys pass over it. And so I sit there and I'm saying, what is it they're talking about? Well, the answer is this is just the this is Kato's inequality, okay? Well, actually, now that I'm on Kato's inequality, let me actually tell you what the improved Kato's inequality is, because the improved Kato's inequality is actually necessary. I was going to tell you what did not work to prove the removable singularities theorem, But now, since we're on Kato's inequality, I'll tell you what the improved Kato's inequality is, okay? And the improved Kato's inequality, and I don't think I'll try to, this is,
So do you inequality on what? On any curvature?
actually it's on any two form. On any two form. So we might as well write it as omega, and it comes from the fact, if you want to look at the covariant derivative doesn't enter at all, because this is a pointwise inequality, and I simply choose a place where the covariant derivative is the regular derivative. And so it's a pointwise inequality, and so the inequality for the regular derivative will actually imply the Kato's inequality for the general case. So. It doesn't mean, I mean, it's the same proof. It's because I can assume A is 0 at a point, and so I can just carry this through. And what the improved Kato's inequality says that the derivative of the norm of omega, okay, is less than or equal to, I think it's n minus 2 over n minus 1, but I don't remember. This constant is less than 1. This is the full gradient now. It's not d. Sorry, there's a square here. No. Yeah, that's the full covariant derivative in the plus d star omega squared. And I think there's might be maybe some curvature terms. But the curvature plus, let's write some curvature terms, because I don't remember whether there are some curvature terms. Oh, no. The curvature, sorry, the curvature's here. If the
You also want the square.
squared. There we go. Okay. So the point is that since okay, so why is this important? This is important. In fact, maybe I'll just use this and because I don't want to go over. And the point is, I already know these estimates on these because I'm in Yang-Mills case, and I have an estimate on this, and I have an estimate on this. And so I can basically, the important part is that it's lower order, and it will actually appear in the inequality on the right-hand side in lower order terms. And so with the improved Kato, then I can take this inequality here and divide by a power of f, and I get, I'll explain to you why this is important. I get Laplacian of, actually, I'll write minus the Laplacian of f, because that's of f to the n minus 2 over n minus 1 is, this is the positive operator, plus f times f to the n minus 2 over n minus 1 is less than or equal to something which I'll just say is lower order. I have a better estimate in that. It's in a better LP space, and I get something like that, okay? So this is now a scalar inequality. It says I have an estimate u, which is f to the n minus 2 over n minus 1, and minus Laplacian of u plus fu minus fu. This is positive operator, so I wrote this, is less than or equal to something which I'll just call lower order. Okay. So it's a scalar Laplacian, and f is small in L2, okay? And so the claim is I can now use the maximum principle. Now, I have to be careful because this is not true at the origin. this inequality is. I know I don't have that. Okay, what do you mean by that? In the sense that why is it not true at the origin? Well, this Laplacian U could have some distributional terms at the origin. And this says nothing about what might come from the distributional terms on at the origin. And that's why we needed a slight improvement. U here is in f to the n minus 2 over n minus 1. And this is at a slightly better, this is in a space that's slightly better than L2. So U is in L2 plus epsilon in 4 dimensions, okay? So I can actually imply the maximum principle. So the maximum principle basically says that U at the origin is, I have a right-hand side, and I solve, I take care of the boundary terms, and I solve the equation with the right-hand side, and I get the, well, let me write it out then. I'm trying to kind of skip. I'll leave improved Katos. So so let's see how we use the maximum principle. So we have Laplacian of U, and I write minus because this is the positive operator, minus f U is less than or equal to something that's lower order. So what I'm working in a disk. It's not global. So first thing I do is I cut off, and I get minus Laplacian of phi U minus f phi U is less than or equal to, and again, I put down something that this is, I'll just write lower order. So that's a cutoff function. It's 1 on the ball of half the radius, and it's 0 outside. Now, solve the problem Laplacian phi minus phi equals the lower order terms, and phi equals 0 on the boundary. Now I have the inequality Laplacian of phi U minus phi minus f phi U minus phi is less than or equal to 0. Well, f is in L2, it's small in L2, and I do a little calculation, and I discover that if phi U minus phi is actually only in L2, I can't apply the maximum principle. I can't assume that phi U is less than or equal to psi. That's what I want to conclude, and that tells me that my curvature is in a better space, because phi was in a better space, so my curvature is in a better space. But I can't apply the maximum principle if this is only in L2. So by improved Kato, I can actually get this to be in a little bit better than phi 2, and a little integration by Partsens and Sobolev constants and so forth tells you that this is true. But remember, we needed this, by the way, is a general technique. Okay, that is, if I get f small in a scale invariant norm, and I get an inequality like that, and I know that this object in here is sufficiently smooth, then I get an estimate on phi U. And actually, this technique works in higher dimensions to prove epsilon regularity. And that's why I actually went through this technique, is that if you actually manage to get f small in a scale invariant case, this inequality will actually, that is, the scale invariance depends on dimension, of course. But you can actually apply this maximum principle to get regularity for F. And so this method of proving the removable singularities is, carries over into higher dimensions, which is why I presented this proof, not the other one. So the point is we get an inequality like this, we apply the maximum principle, and that tells us U is in a better space, which tells us that F is in a better space. And if F is, and it turns out that all we need is to get F in a little bit better space than L2, and then we can actually use a bootstrap argument to get estimates on the maximum norm of F, just from the, well, yeah. So, so anyway, that is, I don't know whether I really helped you or hurt you.
So, thank you.